Thank you very much for the introduction, and thank you for the invitation for this meetup. I'm Inga Jańczuk, as I was introduced, and I work at OLX in Berlin. Today, I would like to talk about A/B testing and quasi-experimentation. And during the introduction, it was mentioned that I have background in economics and econometrics, and it's not without a reason, because I will refer to that during the talk. So without further ado, let's start. To put some context, I'd like to start with a quote. We have a quote by great statistician Leo Breiman. Some of you might know him from his greatest invention of random forests. But in 2001, in a paper, he basically called out that there are two cultures in statistical modeling. One of them assumes that data is generated by some model, by some process, which we want to know. And there's also another culture that just uses algorithmic models and treats the data generating process as unknown. Just put it a bit more visually. You can think about, you can have a look at this slide where you have this data modeling culture on the left and algorithmic modeling culture on the right, and where the first one is more theory driven and the second one is like theory agnostic data driven. Like this first culture is something that we traditionally associate with econometrics and statistics. And the second culture, nowadays we associate more with machine learning. So and in the first, you want to understand how data is generated, and you want to understand what forces drive the outcome. In the second one, what you care about is why. So your model is good enough, is perfect, if it's able to predict why your target variable on some holdout set. That's really all you need. And you just need to know, first of all, realize that there's a difference. And then, you need to know that in this first culture, typical application of the first culture is some causal inference, while the second one is for prediction purposes mainly. And these are not that much interchangeable. There's basically a difference. So to put to visualize, let's say, this problem, let us think about some classic economic problem about prices and sales. So this scatter plot, it shows a typical, or maybe not typical, but some common patterns which you may see in data sets in which you have prices and sales. Just to put it perhaps more into context, you may think about this as prices for hotel rooms, for example. So according to that scatter plot, if the data behaves like it's there, visualized, it would mean that the higher the prices, the higher the sales, basically. And then, if you think of some economic theory or perhaps common sense, if you use common sense, then you may think that this is nonsense, because traditionally, normally how prices work is that when prices grow, basically the sales declines, in terms of quantities, right? Because we have situation of high inflation at the moment, right? So we observe that basically once prices grow, people buy less of certain products, right? But data sets like this are common. Another example, which is usually called out here, is demand for hotel rooms. If you book a hotel in high season, there's wedding season or there's holiday season or any other high season, usually prices are high and also hotels are full. So this is also counterintuitive to what you would expect by some common sense, right? So you may ask why this happens. So this happens because basically we have some other force which is not controlled in that data set. So in our case, that other force is demand. which impacts both price and sales. If you want to put some nomenclature, the demand is called confounder or confounding factor. And basically what it does, it distorts the relationship between price and sales. So just which also makes it impossible. I'll just go back to that graph for a second to call out that if you were to run, like, imagine you're given this data set and you want to you're given a task to say to like examine how sales depends on price. So if you run a simple like model, or it doesn't have to be simple, like any prediction model based on this data, he would come to this wrong conclusion, right? So because of the demand, which is a confounding factor. So now the question is, how could you answer that question? Like, how would you approach this problem? So there's there's an idea that basically you could hold everything fixed and change only the price. And that would give you an answer basically to that problem. Because what really happens in that data set, which I showed before, is that there's no like variation in the data. We observe just some special cases. I also wanted to mention that like traditionally in economics, like this type of problems would be solved with some structural model. So what is a structural model? It's like a model in which you explicitly model like behavior of agents and their preferences. So yeah, basically you use functions to describe people's behaviors. So that would be traditionally done, but for that you need theory, right? You need to like grant that on some economic or any other theory. There are problems with that because like sometimes this model will get complex, and also there are competing theories. Like, yeah, sometimes there's no like single theory that you could use. So there's another potential solution, which could be like randomized trial. So that would work actually perfectly. So imagine that you're a business and you offer your users random prices. So in that sense, you would know like, yeah, it seems perfect solution because once you offer random prices, like you'll have enough variability around like the price variable, while you do not have any consistent bias from other variables like demand, for example. However, there's one problem with that approach, and that is that such an experiment would be incredibly costly for your business. Like actually your business would go bankrupt most likely very shortly, right? Because like, you need to have some sort of price optimization, and you cannot offer random prices to people. So but in general, like experimentation, here's like where I'm coming, is some gold standard. Even though if in this certain case of business and offering random prices, it doesn't make sense, then in general, like experimentation is the gold standard for measuring effect of an action. And in like Silicon Valley, it's been labeled as A/B testing. You may have heard also the term of randomized controlled trials or completely randomized designs. These are not always like identical, but they're similar. And so what is A/B testing or this completely randomized design? It's basically an experimentation technique in which subjects are randomly assigned to control and treatment groups. And I highlighted here like a few words. The main one is randomly. So this is really important, like assumption and important feature whenever you run like A/B testing, that your subjects are really assigned randomly. And that allows you to remove any impact of confounding factors like this demand, which we saw in previously. And in A/B testing, how do we define basics? We always want to measure treatment effects, so like difference between treated and untreated units. So with A/B testing, once you run A/B test, you receive the outcome is so-called average treatment effect, which is defined as here in the equation as expected outcome given the treatment minus expected outcome if there was no treatment. So yeah, average treatment effect is a term to remember. So experiments, gold standard. However, there might be some problems with experiments, so they can be costly or long-lasting or unethical, illegal, and you may name more. So just to give some example, you may think about, for example, you want to, going back to economics, social sciences, you might want to answer or understand what is impact of being fired on overall persons or people's income, like let's say future income. So, of course, you could fire people randomly, right? But it doesn't sound like a good idea to me. This is something that really affects people's lives and is not really, it would not be ethical, right? So, not the best idea. Apart from those reasons I mentioned, there are some other cases, more like technical ones. So when this crucial assumption about randomization cannot be met. So when you cannot split your users randomly, or experiment happened in the past and that the randomization did not have place, or there's dependency between treated subjects. So which should not have place either. So it's important. Then, okay, so we know that A/B tests, even though they are gold standard, there are some problems and you cannot always run it or use it to analyze past events. So here you may ask, okay, so what can we do instead? Can we do anything? So the answer is yes, in some scenarios you can. And you may utilize those so-called quasi-experimental methods, or sometimes they are referred to as near-experimental setups. So what are those? So quasi-experiments are used to inspect past events that resemble laboratory experiments. So they're similar, but some key assumptions are not basically met. And they allow to discover treatment effects under some set of extra assumptions. And those additional assumptions, here's another important term, they are called identification strategy. So whenever you are to run some quasi-experiments, you need to think about, you have, for example, some past data from a natural experiment, let's say. So you need to think what were the conditions under which the treatment was distributed, happened, or And once you have that and you basically clarify your assumptions, this is what you call identification strategy. So what are examples of those quasi-experimental methods which you could use? So the first one that I wanted to call out is difference in differences estimator. Its other name is parallel trend design. And actually both names, they already tell what the method is about. So in order to utilize differences estimator, you need to have two groups of units. One of which is treated, the other one is untreated, and you need to observe them before, after the treatment period. So in this chart, we have our treatment, which happened on November 1st. And as you can see, we do observe both groups before and after the treatment. And what is really key about this method is that both groups, before the treatment period, they must follow the same trend. It means that they must, if one grows, the other should grow. And basically you need to believe or assume that whatever external factors, forces impact your groups, they impact them both equally, right? So hence parallel trends hence parallel trends design. And yeah, you might think about that if you have if you run a business and then if you run it in 2 cities, which are not so far away, then perhaps it might be that basically they behave in the similar way, right? That they are affected by the same economy, but you want to do a change in one of them. I don't know. The change can be really anything. This could be a promotion. This could be a change to some lights which you install in your shop, or yeah. And in that situation, you might expect that basically, because the businesses are similar, and yeah, because they basically are close to each other, but perhaps not too close, so the users do not travel between them. You might basically expect that they would behave in a very similar way. So if those assumptions are met, then you can use the estimator. Here's graphical explanation of what happens, of how this estimator works. And I plot here regression lines for both groups between treatment and after the treatment. And yeah, you can see that basically we clearly see that there was a shift. This is prepared data, right? So in real life, you will not see that most likely that clearly, but here I just use it to visualize the concept. So here we clearly see that after the treatment, level of this treated group changed, right? So yeah, it increased. With differences estimator and its assumption, what happens is that we assume that if there's no treatment, then basically that treated group in the post-treatment period, it would behave like the control group in the post-treated period. So basically the trends would be parallel here. Yeah. And also imagine that this line here, for the control group in the post-treatment period, doesn't have to be an extension of that line in the pre-treatment period. It's not necessarily like that. It could go in any other direction. But then we would also assume that our theoretical line for the treated group would also be parallel to that control trend in the post-treatment period. So yeah, and then your treatment effects is basically the difference, which is here graphically represented. So difference between true realization and that hypothetical value, which is computed with the control trend. Yeah, I'm just checking time. What is beautiful, I would say, about the differences estimator is that it's quite classical statistical method, and it's very easy to compute. Actually, all you need is linear regression, and I haven't put the formula here. So basically, so in order to understand the treatment effects, what you need is to run basically such a model where A is initial level of the control units. Then beta D is the difference between treated and untreated group. Beta T represents the changes over time. And then the most interesting part, and the parameter gamma, which is which is a parameter of interaction between a treatment and treatment period. This is where we are. This is the parameter which gives us the estimate of the treatment. So yeah, that method is pretty simple, still powerful. I have an example here, but yeah, I think I'll just skip. If you have questions, we can talk later. Then I would like to mention about another method, which is synthetic control. So synthetic control was, I want to call out that it was mentioned, it was like labeled as the most important development in program evaluation in the last decade and that was said by Athy and Imbens in one of their articles. Imbens is a Nobel Prize winner in economics. So yeah, that's a pretty big statement. And the method is quite simple and beautiful as well. It is also said that it's a method that has changed social sciences and how causality was like understood in social sciences. I like to think about this as some kind of generalization of difference in differences estimator, because like in the difference in differences, we had just one treated group and one control group. Here in the synthetic control, the idea is that you may create your control group for more than one unit, for more than one group of units. So for example, you may have more than one, let's say, time series, which you may use to come up with this hypothetical scenario, like what if treatment didn't happen, or basically. And that might work better than just simple differences, like just the difference in differences estimator. Basically because here you utilize power of some weighted average, right? Because in real life it might be difficult to find some other unit or other group of units which are basically resemble very closely some other unit of interest. And it might be easier if you want to create like a combination of those. So what is synthetic control? It's like it involves construction of some weighted combination of units, which is used as control, basically. And you want to create that forged control group in such a way that basically before the treatment period, it resembles as close as possible your treated unit. So you may basically ask, like, then how to build that synthetic control group. This is a big question. It's definitely out of the scope of this talk, but you may think about this, like, for example, of creating some weighted average minimizing, which would minimize basically the difference between the value of the treatment group in the treatment period and your synthetic control. But this is like the biggest pinpoint of this method: how to create that weighted average smartly. Once you have your synthetic control, basically what you will be left with is your treated unit in the pre and post treatment period, and your synthetic control. Here I plotted those two lines. You'll actually notice that, like, in the pre-treatment period, they are very, very close. So it looks like my synthetic control is just perfect. And yes, you're right, it's too perfect to be true. In real life, it does not really happen that much. So if perhaps if you see like perfect overlap, you may look for, you may have an overfitting problem, but that really rarely happens, that the lines overlap. Here, as I mentioned before, I use some artificial example. And then how do you basically estimate your treatment effects? You need to look in the post-treatment period, as always. And your treatment effect is basically difference between those two lines. So difference between synthetic control and your treated units. Here also note that the difference is very small. So it's possible that there actually was no or very little impact, but again, it's down to how this example was created. I'm just checking time. 5 minutes left. So the last method I wanted to mention is regression discontinuity. So in that method, what is like key about this is that you can use it when a treatment was distributed along some variable, which we call like running variable. So, which means that there's some variable you may think about that's in like, again, some social sciences context when households which have income below a certain threshold are given some, for example, tax subsidy or some sort of subsidy or tax return, for example. So the thing is that in here, so basically the treatment is not random. We no longer have like groups which have trends or whatever, but as this illustration shows, by the way, this is an illustration from Matt Taddy's book, Business Data Science. This is my favorite data science book. If you don't know it, I totally recommend. It's very insightful, and it actually looks into like how to approach some common business problems with data science and economics as well. So worth reading. So here in this regression discontinuity, our running variable is basically on the x-axis, and our treated here's the treatment line, right? So in that case, our treatment was around value of the running variable 0. And how do you basically approach? How do you approach the estimation of the treatment effects? Is that you need to understand what was the level of sorry, I'm trying to be fast, but what you need to understand what's the level of your outcome variable near the threshold, right? Because that's the key assumption. Because we assume that individuals near the threshold are very similar. So because they are near the threshold, and basically what you need to estimate like the value of those individuals near the threshold, below the treatment threshold, and above that. There's some different methods how you can do that. Like the simplest one, you can just take an average, for example, right? And that would be one way. You can fit a regression line on this very small range of threshold running variable. Yes, and it's important also to mention that with that method, you can estimate only local treatment effects. Because as you run your estimation near the threshold, they are really local. So if the variable, if the threshold around the running variable would be set at different place, then the results would be totally different. These are like all the 3 methods which I wanted to mention today. So just to sum up, here are some key takeaways. So basically, I wanted to like reiterate this cliche statement that basically prediction and causality are not the same, and correlation does not imply causation. These are different things, and they should not be like mixed. And if you run like a prediction model, be mindful that it's not with prediction model, you do not model the forces which impact the data generating process. And if you care about why, it doesn't mean that you care about causality. So that's I think important. Then counterfactuals. So what we just described, rather than predictions, are critical for policymakers, like in social sciences. Then A/B testing and experimentation in general is gold standard for identifying causal effects. In some cases, A/B testing cannot be used. And sometimes in those scenarios, there are some alternative quasi-experimental setups that can be useful. And quasi-experiments in general allow to make use of past events that resemble laboratory experiments. Sometimes you may just last final note that it's usually used to analyze past events, but sometimes in some scenarios you may want to design actually a future experiment which utilizes those quasi-experimental frameworks. And that's it. I included some references, and thank you.